Welcome to our series on structural dynamics and engineering vibration, based on the book by Dr. Dan Inman. Today, we're diving into the fascinating world of vibration, a phenomenon we encounter every day, whether we realize it or not. Vibration is all around us. From the pleasing sound of a vibrating guitar string to the unwanted shaking of an airplane frame that could lead to fatigue and structural failure. Vibration is the repetitive motion of objects relative to a fixed point, and it plays a critical role in engineering design, sometimes helpful, sometimes harmful. Take cars, trains, and even bicycles, for example. These systems have built-in devices like shock absorbers to reduce vibration and ensure a smooth experience for the user. But what exactly causes vibration? It's the interplay of potential energy stored in springs or structures, and kinetic energy, the energy of motion. This energy exchange creates the motion we call vibration. In this series, we'll explore how to mathematically model and predict vibration. For instance, if we analyze a pendulum, we notice its motion over time closely matches a sine wave, a fundamental tool we'll use throughout this course. Using Newton's laws of motion, we can derive equations that describe the pendulum's movement. These equations not only predict its motion, but also tell us how long it takes for the pendulum to complete a cycle. A perfect example of how observation and mathematics come together. Before we dive deeper into the subject, remember, vibration analysis builds on your knowledge of dynamics, system dynamics, strength of materials, and calculus. Together, these form the foundation for understanding more complex systems. In this first chapter, we'll focus on free vibration, where no external forces act on a system. We'll uncover key concepts like natural frequency, the rate at which an object vibrates on its own, and learn to model these vibrations mathematically. Let's explore free vibration and learn how to derive the equation of motion for a simple pendulum. Our goal is to derive the equation of motion step by step and uncover the natural frequency that governs its behavior. Picture a small mass, m, suspended from a fixed point by a string of length L. The pendulum swings back and forth in a plane, making an angle alpha of t with the vertical at any given time t. Two main forces act on the pendulum: the force of gravity, pulling the mass downward, and the tension in the string, keeping the mass constrained along the circular arc. Our goal is to derive the equation of motion for this system. The force responsible for the pendulum's swing is the tangential component of gravity, given by this equation. This restoring force always acts to bring the pendulum back to its equilibrium position. Using Newton's second law for rotational motion, for a simple pendulum, the moment of inertia about the pivot point is I equals ml squared. Substituting the torque caused by gravity gives us the equation. The negative sign appears because the torque acts in the direction opposite to increasing alpha, meaning it is a restoring torque. Simplifying, we find the angular equation of motion. This is the nonlinear equation of motion for the pendulum. For small angles, where alpha is measured in radians, we can approximate sine of alpha approximately equals alpha. This linearizes the equation. This is the linear equation of motion for the pendulum, describing its oscillations when the angles are small. This term is the natural frequency, which determines how quickly the pendulum oscillates. This is the general solution for this motion. This solution describes the periodic harmonic motion of the pendulum under small oscillations. In this lesson, we explored a single degree of freedom system. In the upcoming chapters, we'll dive deeper into topics such as response to harmonic excitation, general forced response, multiple degree of freedom systems, and other key concepts that shape our understanding of vibration dynamics. Just like the pendulum, life is a continuous exchange of energy, ups and downs, moments of stillness and motion. But through it all, balance is key. In physics, in nature, and in our own journey, understanding the forces that drive us helps us navigate challenges and appreciate the rhythm of life. Don't forget to like, subscribe, and share to stay updated. Keep learning, keep exploring, and find harmony in the motion of the world around you.